This video goes with our 22-1 lesson video. And the first question is, what is current? And current occurs when charge is allowed to move. So here we have a picture of a D-cell battery connected up to a light bulb. And what happens here is that we have the negative side of the battery, and these electrons that are on this negative side of the battery don't want to be next to each other. And the electrons have a place to flow. They have a place to go. And there's a positive side of the battery over here, and so these electrons will travel through the light bulb, lighting the light bulb, and going to the positive side. And so current is allowed to flow. We've given a path for those electrons to flow. So what we have here is this is called a capacitor, but you can think of a battery having a negative side and a positive side. And so these negative charges want to flow through the battery or flow through the light bulb over to the other side. So current is when charge is allowed to flow or allowed to move through a circuit. The way that current is created is by setting up, in this case here, setting up a potential difference between 2 points. So for current to flow, there has to be this potential difference. And a potential difference is just having what we have here, a negative side of a negative plate and a positive plate, and just creating an area for charge to flow. The variable you'll see for potential difference is delta V, and that can be set up by a battery, it can be set up by a power company, and there's just different ways of making sure that there's a negative or low potential and then a higher potential. The next question is, what is conventional current? And although it's electrons that we show for our current previously, actually conventional current is when we show positive charges moving. So although it is electrons which are the mobile charge carriers, which are responsible for electric current in conductors such as wires, it has long been the convention to take the direction of electric current as if it were the positive charges which are moving. And this is due to Ben Franklin when he was working with charges and current and so on. He didn't know about electrons, and he said that current was the flow of positive charge. So that's the way we've always, in high school classes, have always looked at current, and that's called conventional current. And that's the way we're going to look at it in this class. So when we look at this, we're not going to look at the flow of electrons. We're actually going to look at the flow of positive charges. We're going to talk as if the positive charge flowed, and that our current is actually going to follow this from the positive to the negative. Even though it's electrons that flow, we're going to talk about current as if it's flow of positive charge. This is also done because if you remember, electric fields are drawn to show the direction a positive charge will flow. So if we were to draw the electric field in this battery or in these wires, electric field in these wires would show this. And so the current is drawn in the same direction that the electric field is drawn. There's electric field lines all through this wire, and the current flows in that exact same direction. Electric field is drawn to show the way a positive current will flow, and so current and electric field are in the same direction here. Our next question, question number 4, is what is conservation of current? And conservation of current is just what it sounds like. The amount of current coming in equals the amount of current coming out. So what we have here is input currents equals output currents. That's conservation of current. So we see this current coming in, and it splits up into 2 pieces. Or we have these 2 pieces coming in, they come together here. And so the amount of current coming into a junction equals the amount of current coming out of the junction. So we have an example of that here. In this problem here, we can figure out what current is right here in this section. So if you look at it, we see that there's 7 amps going in, and there's 8 amps coming out. So we need to have 1 more amp going in to make this 8 amps going in compared to 8 amps coming out. That's just that straightforward idea of conservation of current. You can also think of this as conservation of charge. The amount of charge coming in equals the amount of charge coming out. This is useful for situations like this, where you have current coming out of this positive side here, and it actually splits up. Comes along, and then comes back together right here, goes through this bulb, and comes back to the negative side. And so if you had to guess which bulb is the brightest and which bulbs are the least bright, what would you say? So pause the video and think about which bulb's the brightest and which is not as bright. The bulb that's brightest is bulb number 1. That's the brightest because more current is going through that bulb than any other bulb. Bulb 2 and bulb 3 are less bright because they have half the current going through them. Now we're on question 5. What is the equation for current? The equation for current is I equals Q over T. I is the current. It's measured in amperes. Sometimes you'll see it as amps, and we'll write it as A. So you might have something like 5 amps or 5A. Q is the charge. That's measured in coulombs and has the variable C. And T is time. That's in seconds. And so what 1 amp equals 1 coulomb per 1 second. So in current, if you have an amperage of current flowing, that means 1 coulomb of charge will pass a given point each second. If you were counting the number of charges going by, you would count a coulomb of charge in 1 second. The next question is, what is EMF? And EMF is short for electromotive force. And the variable is a script E, and it's measured in volts. And what it is it just gives you what the battery voltage is. EMF is just a way of saying, just giving us what that battery voltage is. It's just basically that. So it's how many volts your battery is. And so you'll see up here that EMF is the potential difference of the battery. It's the voltage. And then we also have what is the charge escalator model of a battery, and that's what this is right here. So what happens is these positive charges here come out of the battery, follow the electric field, and come along and come back into the negative side of the battery. They like being on the negative side. But you have this positive charge right here right now, and how do you get it back? It's over by the negatives. How do you get it back up to where it's supposed to be, up at the positive? Well, there's this charge escalator model, and what happens is the chemical reaction within this battery does work on this positive charge, lifts it up, does work, gives it energy, and puts it back into the circuit. And so if you read this, it says the charge escalator maintains a constant potential difference between the terminals of the battery. And the way that's done is with that chemical reaction within inside that battery takes those positive charges and pushes them to places they'd rather not be, up in this positive area. But then they're released into the circuit and they flow through that circuit. It's very similar to lifting a bucket of water up, carrying it up a hill, and then pouring it down the hill, letting it run down the hill, and then gathering that water, and then lifting it back up to the top of the hill, and then letting it pour down. The work that you're doing by taking that water and lifting it to the top is the same as the chemical reaction lifting the positive charges so they can fall through the circuit. So in this picture here, you can see that the charge falls downhill through the wire, but it can be sustained because of that charge escalator. These positive charges don't just gather here at the negative site. They don't just stay down here at the negative part. They get lifted up. Just like you can carry water up to the top of a hill, the chemical reaction within the battery lifts these charges up to the top. Now, when I said that they're doing work, we have this equation right here, that there's a change in potential energy. The work that's being done is causing a change in potential energy to occur, and that equation is Q times delta V. It's the charge times the potential difference. It's very similar to force times distance. In this case, it's charge times potential difference. So the work that's done gives it a change in potential energy, gives that charge a change in potential energy, and so you just multiply the charge times the potential difference to see what that change in potential energy is. That the negative terminal is at potential energy equals 0, and that positive terminal is at potential energy equaling Q delta V. So our next question is, how is the flow of water similar to the flow of current? Well, if you look at this picture here, you see water flowing through a pipe, and then it's turning this turbine and coming back out. The amount of water coming in equals the amount of water coming out. Well, this is the exact same thing. The electrons coming in do work on the light bulb, just like the water did work on the turbine. But the electrons don't get used up. They keep flowing through the bulb back to the battery to complete this cycle. If you look at this picture here, it really does a nice job of showing that the battery over here is lifting these charges up. It's doing work. And then it's at this high point here where the charges then fall through the circuit and then do work on this resistor here, like a light bulb might be, this paddle here, falls down to the circuit, flows through the rest of the circuit back to the battery, and then gets lifted up. So this is how water and charge is very similar. The flow of water and the flow of charge can be very similar to each other. So we want to do a couple problems here. Page 723, number 2, we'll take a look at now. So this problem says 2 times 10 to the 13th electrons flow through a transistor in 1 millisecond. What is the current through the transistor? So I have the information written here, and we know the equation I equals Q over T. We have our time here, 1 times 10 to the negative 3 seconds, but I need to figure out what charge that number of electrons is. So we've done this before. We'll figure out what the charge is. And we know that 1 electron is equal to 1.6 times 10 to the negative 19th coulombs. We'll just multiply that by the 2 times 10 to the 13th electrons that we have. And we come up with a charge of 3.2 times 10 to the negative 6 coulombs. So we just go ahead and plug that in down here. And we come up with our answer of 3.2. And if we do times 10 to the negative third coulombs per second, or in other words, amps. And that's our answer. Now you want to look at page 723, number 12. Actually, I'm going to skip 12. I'm going to go to 14 because we did a problem similar to 12 earlier in the video. So in number 14, it says, what is the EMF of a battery that increases the electric potential energy of 0.05 coulombs of charge by 0.6 joules as it moves it from the negative to the positive terminal? So I've written down all our givens here, and we have to realize that EMF is the exact same thing as a potential difference, delta V. And so we use our work equation, or our change of potential energy equation, is Q delta V. And so our change of potential energy, that's 0.6 joules, equals 0.050 coulombs times delta V. And so our EMF, or our change of potential, equals 12 joules per coulomb, which is the same thing as a volt.